Sorry about the interruption. Looks like I said, I'm quite a bit more popular than I expected. Back to water. Water, as you can see, has hydrogens on the top and no hydrogens on the bottom. Well, the question is, wait a minute. If nature is balanced, then there should be a hydrogen on either side. And that's not true because of the repulsivity of the electrons, one for the other. Notice that the electrons push the hydrogens apart. They're not close together up there. And these two pair of electrons down below, again, stay as far away from each other as they possibly can. They don't like each other. Electrons are repulsed. This gives the water a shape. We call it a polar molecule. And this polar molecule has some really unusual effects in nature. One of those unusual effects in nature is, in fact, the characteristic of attracting another kindred molecule. In other words, the negative side has a tendency to attract the positive side of another water molecule. This polarity is extraordinarily important in nature. Now, I always give some examples for something that students can do. Go get a couple of drops of water, probably 2 or 3, from a dropper, and put it on a flat plate and run your fingers through it slowly. The tendency will be the water will follow itself. In other words, you draw it along because the water molecules are attracted for one another. Another thing about water is that its attractiveness allows it to be really quite resistant, if you wish. And this resistance is, in fact, something that you're familiar with. When you go swim, you jump into the water, and by all rights and purposes, you have a greater density in water. You ought to sink like a stone. But you don't. As a matter of fact, if you know how to float, you can turn on your back and stick your arms out, spreading your mass out to as great a volume as you can and float on the water. Well, that would seem possible. But that property of water, again, a continuation of polarity, is called surface tension. Now, surface tension, you can actually find yourself a container of water, fill it about 3/4 full of water, put it someplace where it's very still, get a paper clip and unfold the paper clip to where it's unfolded completely, and then make sure it's level across. Take yourself a pair of tweezers and put the paper clip to where it just touches the surface of the water. If you do it right, it'll float. Now that's defying what most of you understand as the rules of nature. It's a high-density substance, probably some kind of steel, floating on something that's very low density, which is water. That, again, is the resistance of the surface tension of the water to the metal being spread out. Now, how does this come out in nature? If you've ever been to the giant redwoods, they're quite spectacular. Go up a couple 100 feet in the air. They have a root system, which is only about 15, 20 feet deep, but still, it's a very long way to put water. The polarity of the water, called capillarity, draws the next water molecule up. You know there's no series of squirrels on the side of these huge trees with their pinwheel pumping that water up and down in the tree. So it's got to come from somewhere. And the force of nature, which I find one of the most fascinating, is that when a drop of water evaporates from the topmost leaf, another drop, another molecule, I said drop, I meant molecule, another molecule of water is drawn up. So think about that. You know what gravity is like. You jump off the top of a 200-foot building, you're going to splat. So there's that much force drawing against gravity to bring that water to the top of the tree. So I think capillarity, in my far from humble opinion, is one of the most important features and characteristics of water and of nature, in fact. Now let's go back to the electron configuration. On the left, you see hydrogen has one electron, and it fills in, obviously enough, the first shell, 1s. Now, to fill that shell, you need 2 electrons. All the s shells need 2 electrons to be full. So you fill that, and you have the next element called helium. Well, in a full shell, that means it's not reactive. And helium, as you find out, is a non-reactive substance called an inert or non-reactive. The next element, 3, has the 1s, and the 2 indicates there's 2 electrons in 1s, and then the 2s. Okay, the electron is shown. The 4s, the fourth element, has 1s2 and 2s2, and you immediately say, okay, that's full, it should be inert. But not true. The second shell has 2s and 2p, which has a capacity of 8 electrons. So that allows you to go to the fifth element, which has 1s2, 2s2, and 2p1, which is in the x suborbital, x, y, and z. Now the next one will fill the y, and the next one will not fill the y, but put an electron in the y. And then the next one will put electron in the z, and then go back and fill the x, fill the y, fill the z. Now, how many elements have we covered here? Well, 2 for the 1s2 and 2 for the 2s2. That's 4 elements. And then 6 for the p shell. So we, in fact, have covered 10 elements electron configuration when we fill the pxyz. I thought that would be interesting to you. So you see how the electrons actually work. They're quite flighty and very difficult to put your finger on because they move so fast that they have wave-like characteristics as well as particle characteristics. The wave characteristics, think of something like a wavelength of sound. So the wave characteristics of high-speed particles, very important. The faster you go, the greater the wave characteristic and the lesser the particulate characteristic. That's found in physics for all you physics folks.